soil, and water pollution is a serious problem worldwide. Pollution is the largest existential threat to humans, killing more than 9 million people each year, which represents about 15% of all deaths globally. Pollution also causes many disabilities, and therefore impacts our ability to live and enjoy a normal life. Pollution is also costly. Welfare losses due to pollution are estimated at more than 4.6 trillion euros per year. In Europe alone, there are more than 2.5 million potentially contaminated sites. Classical remediation is based off of methods such as excavation and off-site disposal, which have high costs associated. In Europe alone, to 6.5 billion euros per year. Microorganisms, however, are sustainable alternatives that can be generally used in techniques called bioremediation.
What works in bioremediation is to boost the local or introduced microbes to be more efficient in degrading pollutants. The microorganism can be fungi, bacteria, or algae. One important approach consists in correcting the environmental condition to create a comfortable environment for the selected microbes that, in turn, degrade pollutant both in soil and water. Interestingly, proper bioremediation processes rectify most situations in relatively short time and in a suitable way.
Thanks to advancing technologies, bioremediation is also economically viable compared to chemical and physical remediation strategies. Hence, bioremediation is becoming the main strategy to recover contaminated sites all over the world. But why are bacteria, fungi, and algae so effective in degrading pollutants? Well, during evolution, some microorganisms, such as many fungi, evolved and acquired the ability to degrade recalcitrant natural compounds such as lignin.
By producing highly specific oxidative enzyme, these microorganisms can degrade the numerous pollutants such as pesticides, herbicides, aromatic and aliphatic hydrocarbons, detergent, personal care products, and drugs. Microbial consortia, consisting of different fungi, bacteria, and in case of water of algae, are generally more effective than a single microbe in bioremediation. This is due to multiple production of oxidative enzyme and other molecules such as biosurfactants.
Algae are also playing an important role in water bioremediation, as they can absorb and accumulate heavy metals, nitrogen compounds, and other contaminants in water. Through their specialized metabolic pathways and photosynthesis, they become important areas in the purification of polluted waters, significantly improving the water quality and the health of the aquatic ecosystems.
One of the most pressing environmental threats nowadays is the massive pollution by plastic debris in soil and water worldwide. Millions of tons of plastic is produced and released into the environment every single year, damaging soils and oceans. Current plastic production worldwide is around 460 million tons per year, and just around 50% of that plastic is used once and thrown away. Did you know that plastic pollution has created the Great Pacific Garbage Patch, a plastic aisle 3 times the size of France?
Moreover, microplastic can be even more hazardous. In agricultural soil, plastic pollution reaches on average concentration around 310 items per kilo. These not easily biodegradable plastic create a new environment, the plastisphere, in which complex microbial communities develop and evolve new mechanisms to degrade them. Bacteria, fungi, and algae are indeed the most powerful tools to solve this environmental emergency. Many research teams are working on the selection of microbes capable of degrading different types of plastic.
So, how do we select these microbial superheroes that degrade contaminants? Well, by isolating them from the contaminated environment. Alternatively, we can use microbes already identified and preserved within the microbial biobanks.
The isolates are then screened for different properties like the ability to use pollutant as carbon source, the ability to survive in contaminated environment, and the possible synergy. Here, for example, you can see some fungi isolated from a polluted soil that are growing on different hydrocarbons as soil carbon source. And here you can see fungi isolated from plastic. Afterwards, we start to study the degradation pathway and many other phenotypical traits, testing the bioremediation capability in microcosm, mesocosm, and finally in fields.
MIRRI, the microbial resource research infrastructure, provides a step forward in biotechnology and bioeconomy by combining microbial collections with real-life innovations.